Welcome to The Explainer. If you've ever had to wrestle with some of the more advanced networking stuff in Kubernetes, it can get real complicated, real fast, right? I'm talking about those situations where you're not just spinning up a simple web server, but you need specific hardware, maybe a super fast network card, or you absolutely need guaranteed performance for a database or an AI workload. It's in those moments that the cracks in the standard networking model can really start to show. Well, today, we're going to dive deep into a new technology called Dynamic Resource Allocation, or DRA for short. And let me tell you, it's not just another tool. It's poised to completely change the game. We're talking about a fundamental shift in how Kubernetes even thinks about and manages resources. So we're going to break it all down, what DRA is, why the old way of doing things is hitting a wall, and how this new approach finally gives us that fine-grained, user-driven control that, frankly, we've all been searching for.
Okay, so here's our roadmap for this masterclass. First, we have to set the stage. We'll start by digging into the foundational limits of the tool we all know, the Container Network Interface, or CNI. Then, once we understand the problem, we'll introduce the solution, DRA, a whole new paradigm. After that, we'll look at how these two worlds, CNI and DRA, are being brought together and what new superpowers this combination unlocks. We'll then see it all happen live in a guaranteed bandwidth demo. And finally, we'll zoom out and talk about what this all means for the bigger picture, the very future of native networking in Kubernetes. So, let's get into it. All right, first up, let's talk about CNI's foundational limits. To really appreciate where we're going, we first have to have a crystal clear understanding of where we've been. So we're going to start by looking at the original tool for container networking, CNI, and really pinpoint the exact spots where it starts to break down under the pressure of modern, complex applications. It's about a shift from a rigid tool for an admin to a flexible device for a user.
So, at its very heart, what is CNI? It's a simple and honestly, a brilliant contract. A cluster administrator writes a configuration file, usually in JSON, that says something like, I want this kind of network using this plugin with an IP address in this range. Then, when a pod needs to be created, the container runtime on the node just takes that configuration file and hands it off to a CNI plugin binary. The plugin does its work, and presto, the pod has a network. It's a very straightforward, very deterministic, you get exactly what I, the admin, told you to get model. And for simple, homogeneous setups where every node is the same and the admin knows everything up front, this works beautifully. But what happens when the real world, in all its messy glory, comes knocking?
This is where that rigid, deterministic model starts to show its age. Let's really break these points down. First, heterogeneous clusters. Imagine a cluster that's grown over time. Some nodes have 10 gigabit NICs, newer ones have 100 gigabit NICs from a different vendor. You can't have one single static CNI configuration file that works for both. The admin is forced into complex workarounds. Then there's advanced hardware. What if your high-performance computing app needs a specific hardware feature, like RAW for low-latency networking, or it needs to be placed on a NIC that's on the same NUMA node as its GPU to avoid performance-killing latency? The CNI spec has no language for that. The user, who knows their app needs this, has no way to ask for it. Then there's dynamic availability. You can't just say, hey, give me any available 10 gigabit port. No, you have to ask for a specific interface by name. And if another pod is already using it, tough luck, your pod fails to start. It all comes down to one core problem. CNI is entirely admin-centric. It presumes the admin knows everything about every workload's needs in advance, which is just not realistic. The user, the person who actually knows what their app needs to perform well, has no voice in this process.
And this brings us to the core conceptual shift that underpins this whole discussion. The old view, on the left, sees networking as purely an administrative task. The admin sets it up, and pods consume it. But the new view, on the right, is a total game changer. It treats a network card not as infrastructure, but as a user device, a resource that an application developer can request with specific attributes, just like they'd request a GPU or a specific amount of memory. This fundamentally changes the role of CNI. It's no longer just a generic tool for configuring a network. Its new job is to prepare a specific device that has been dynamically allocated directly to the user's pod, removing from that static, top-down, one-size-fits-all model to a dynamic, user-driven, and on-demand one.
Okay, so now that we've thoroughly diagnosed the problem, let's turn our attention to the solution, Dynamic Resource Allocation, or DRA. Now, for a minute, I want you to completely forget about networking. Just put it aside. DRA is a general-purpose framework. It could be for GPUs, FPGAs, special accelerators, or, yes, network cards. Understanding how DRA works at a fundamental level is the key that unlocks everything else we're going to talk about today.
To really see why DRA is such a leap forward, let's compare it to the old way of doing things with the device plugin framework. Before DRA, on the left, the Kubernetes scheduler only saw really simple counts. It would know this node has 8 GPUs, but that's it. It didn't know their models, their features, or if they were already in use in a specific way. So it would just place a pod on that node based on that simple count. Only after the pod was scheduled would the kubelet on the node call a device plugin to pick a specific GPU. The scheduler was basically flying blind, making a placement decision with very limited information. Now, contrast that with DRA on the right. The whole process gets way smarter. A user makes a rich, attribute-based request. I need a GPU of this specific model with this much memory and this specific feature. The scheduler then has a direct conversation with DRA drivers running on the nodes to find a specific device on a specific node that perfectly matches that request. And here's the kicker. It reserves that device before the pod is even scheduled. All the intelligence moves up from the node into the scheduler, enabling much smarter, cluster-wide, and aware placement decisions.
This entire intelligent process works like a beautifully choreographed 3-act play. Act 1 is publish. A special DRA driver running on each node scans the local hardware. It discovers all the available devices and their specific attributes, and then it publishes this inventory to the Kubernetes API server. This inventory is called a resource slice. Think of it as creating a detailed catalog of every resource available in the cluster. Act 2 is request and schedule. This is where the user comes in. They create a pod, and inside that pod, they define a resource claim that describes exactly what they need in great detail. Now the scheduler steps in and acts as a matchmaker. It scours all the published resource slices to find one that perfectly fits the user's resource claim. Once it finds a match, it reserves that specific resource and only then schedules the pod onto that specific node. Act 3 is allocate and configure. The pod lands on the chosen node. The local DRA driver on that node is then notified. It looks at the reservation details from the resource claim and performs the final low-level setup to make that specific device available inside the pod's environment. It's a clean, declarative, and fully orchestrated flow from start to finish.
So let's get concrete and look at the actual Kubernetes objects involved. Starting with the user's side of things, the request. It all begins, as always, with the pod manifest. As you can see on the left, inside the pod spec, we have a new section called Resource Claims. Now notice the pod isn't asking for a resource directly. Instead, it references a claim by name, in this case cat1, and it points to something called a resource claim template. Now look to the right. The resource claim template is where the real magic happens. This is a reusable template that defines the kind of resource we want. Inside its spec, we have requests, and this is where we define the specific attributes we're looking for using powerful selectors. In this fun example from the source presentation, we're using the Common Expression Language, or CEL, to say we need a device where the attribute color is exactly equal to black. This is how we express those rich, detailed requirements. We're not just asking for one cat. We are being extremely specific and asking for a large black cat.
And here's the other side of that marketplace, the supply. This is what the DRA driver on a node creates. It's called a resource slice object. Think of it as a classified ad posted to the entire cluster. It clearly states, hey everyone, I'm example node and I have a device available named Dev0. And here are its attributes. Its color is black and its size is large. This resource slice is the exact inventory, the detailed catalog, that the scheduler will browse through to find a match for our user's very specific request.
So after the scheduler, our diligent matchmaker, does its job, it finds that the resource slice on example node is a perfect match for the request coming from our pod with cats. At that point, a resource claim object is dynamically created from the template we saw earlier, and its status is updated to reflect this successful match. This is the crucial final piece of the scheduling puzzle. Just look at the status section. The allocations field couldn't be clearer. It states that the device named Dev0 has been allocated. And just as importantly, the reserved for field creates an explicit, unbreakable link. It shows that this specific device is now reserved exclusively for our pod with cats. This completes the declarative loop. We have a clear, auditable, API-driven record of who asked for what was available in the cluster, and what specific resource was ultimately allocated to fulfill that request. No guesswork, no ambiguity.
All right, so we've established our two main characters in this story. CNI, the veteran expert at network configuration, and DRA, the brilliant new system for dynamic resource allocation. Now for the most important part of the plot. How do we get them to work together? This is where a new component enters the stage, the CNI DRA driver, and its entire purpose is to act as the bridge between these two powerful worlds.
So the crucial point is how this connection actually happens on the node. In this new world, the container runtime like Containerd no longer calls a CNI plugin directly for these advanced secondary network interfaces. Instead, this new component, the CNI DRA driver, slots itself in as an intermediary. It registers itself with a container runtime as a plugin using a nifty piece of tech called NRI, the Node Resource Interface. This registration gives it the power to intercept pod lifecycle events. So when a pod is about to start up, the runtime effectively pauses and notifies the CNI DRA driver. The driver then springs into action. It looks at the resource claim that's been associated with that pod to see exactly which network device was allocated by the DRA scheduler. Armed with this definitive information, it then makes the concrete, low-level call to the appropriate CNI plugin to perform the final network setup. It's the essential translator between the high-level, declarative DRA allocation and the low-level, imperative CNI configuration.
Now, this unified approach brings two massive, absolutely game-changing benefits. First, as the slide says, it's unified. In the old world, managing advanced networking was often a split-brain operation. You might use one tool like an SR-IOV device plugin to allocate the raw network device, and then a completely separate tool like Multis to actually configure it. It was disjointed and often brittle. With the CNI DRA driver, it's all one cohesive, seamless flow. The same system that understands the high-level allocation is also responsible for the low-level configuration. Second, and this is just as important, it's declarative. Because we're using native DRA objects like resource claim, the entire network request becomes a first-class citizen of the Kubernetes API. This means we are finally free from the tyranny of stuffing complex, unstructured JSON configuration blobs into pod annotations. And by being a native API object, we get all the incredible benefits of the Kubernetes API machinery for free. Strong validation, rich tooling support, and a clear, consistent user experience across the entire ecosystem.
Now, using the core DRA framework for networking is a fantastic first step. But as we all know, networking is special. It has unique requirements that other devices don't. For example, it's not enough to just allocate a network device. We absolutely need to know what IP address it was assigned. And often, we don't want to dedicate an entire expensive NIC to one pod. We want to share it and maybe claim just a portion of its bandwidth. These specific needs led the community to realize that DRA itself needed to be enhanced. So let's look at two key Kubernetes enhancement proposals, or KEPs, that add this crucial network-specific context.
The first critical enhancement is all about creating a feedback loop. It's called KEP 4817, and its whole purpose is to enrich the status of the resource claim object. Before this KEP, the status would tell you that a device was allocated, but it wouldn't tell you much else about it. This KEP introduces a new, structured devices field directly into the status. This provides a standardized, predictable place for the driver to report back exactly what it did during the configuration phase. For networking, this is an absolute necessity. It's the mechanism the driver uses to say back to the cluster, "Okay, I configured that device you allocated, and by the way, here is its MAC address, and here is the IP address I successfully assigned to it." This structured feedback is not just nice to have, it's critical for troubleshooting and for allowing other controllers and systems in the cluster to understand and react to the pod's network state.
And here is what that rich feedback looks like in practice. This is a snippet from the status of a resource claim object after KEP 4817 has been implemented. You can immediately see the new network data field. This is pure gold. It contains the hardware MAC address, the name of the interface as it appears inside the container, in this case net1, and most importantly, the IP addresses that were assigned. Now, take a second and imagine the powerful possibilities this unlocks. A component like the endpoint slice controller, which is what actually backs Kubernetes services,
could now be taught to look at this field. Instead of only creating services for the pod's primary IP address, it could read the IPs from this network data block and automatically create service endpoints over these secondary high-performance networks. This would natively integrate them into the entire Kubernetes service discovery ecosystem, which is a huge deal.
The second major enhancement, KEP 5075, is all about sharing and implementing quotas. Many of the most valuable resources, especially in the networking world, aren't single indivisible units. Instead, they represent a pool of finite capacity. The most obvious and universal example is bandwidth. A 100 gigabit network card has, well, 100 gigabits per second of bandwidth. This KEP introduces a brand new concept to draw called consumable capacity. It allows a single physical device to be marked as shareable, and for its finite capacity, like that bandwidth, to be advertised to the cluster and then consumed or checked out by multiple different resource claims until it's all used up. This is the absolute key to enabling the use case of guaranteeing a specific slice of a shared resource to different pods running on the same host.
And this whole system works as a clear, two-sided contract between the driver and the user. On the left, we have the driver's resource slice. You can see it's advertising a device named ENP0S10 and has set shared true. Critically, it also declares a capacity, in this case, bandwidth, 10 GI. So it's telling the cluster, I have 10 gigabits of bandwidth to share. Then on the right, you see the user's resource claim template. The user makes a request under a new capacities field asking for a minimum of bandwidth 5 GI. The scheduler then acts as the accountant. It sees the 10 gigabits total, it sees the 5 gigabit request, approves the allocation, and immediately debits the node's available capacity. It now knows that there are only 5 gigabits left on that node for the next pod that comes along.
All right. Theory is great, and looking at YAML is definitely illuminating, but there's nothing quite like seeing it work. So now let's walk through the demonstration from the presentation that puts all of these complex pieces together. We're going to see that exact concept of consumable capacity in action to provide real, guaranteed shared network bandwidth. This is the moment where all the concepts, DRA, resource slices, claims, and K5075 all converge to solve a real-world problem.
Okay, here's the setup for the demo. It's simple, but very effective. First, the environment. We have a small cluster with 3 worker nodes. The key detail is that worker 1 and worker 2 each have a special 10 gigabit per second network interface. Worker 3 does not have the special hardware. Second, the resources. Our CNI DRA driver is running, and it has created resource slices advertising that 10 gigabits of shareable bandwidth is available on worker 1 and worker 2. There are no such slices for worker 3. Third, the requests. Now we're going to intentionally oversubscribe the cluster. We'll deploy pod A, which asks for a full dedicated 10 gigabits. Then we'll deploy a set of 3 pods, let's call them pods B, where each one requests 5 gigabits. So that's a total request of 10 plus 5 plus 5 plus 5, 25 gigabits of bandwidth. But remember, we only have a total of 20 gigabits available in the entire cluster. Let's see how the scheduler handles this.
After we deploy our pods, this table shows the result. Let's break it down line by line, because this is where it all comes together. First, demo A, the pod that asked for a full 10 gigabits, landed successfully on kind worker 2. It's now running, and it has consumed that node's entire 10 gigabit capacity. Next, 2 of the demo B replicas landed on kind worker. Since each one asked for 5 gigabits, together they have perfectly consumed that node's full 10 gigabit capacity. And now, we come to the most important line on this slide, the third replica of demo B. Its status is pending. It has not been assigned to any node. It is stuck, waiting.
And this is the million-dollar question that proves the entire system works exactly as designed. Why is that last pod pending? It's not a bug, it's not an error. It is the correct intended behavior. That pod is pending because the DRA scheduler is acting as that intelligent accountant we talked about. It is fully aware of the consumable capacity across the entire cluster. It knows that the 10 gigabits on worker 2 were completely consumed by pod A. It knows that the 10 gigabits on worker 1 were completely consumed by the first 2 pod B replicas. And it knows that worker 3 has no capacity of this type to offer at all. There is simply no node left in the cluster that can satisfy a 5 gigabit bandwidth request. The scheduler correctly identifies the situation and leaves the pod in a pending state until resources free up.
This provides true, hard, predictable guarantees. You get what you ask for, or you wait.
This new capability is obviously incredibly powerful, but as with any major leap forward, it also opens up a whole new set of very challenging questions and passionate debates within the community. So, to wrap things up, let's look at the road ahead. We'll explore the tough discussions that are happening right now, the challenges that still remain, and the tantalizing possibility of what the future of native networking in Kubernetes might look like.
A huge and still unresolved discussion is how to best integrate this new DRA approach with the vast, diverse ecosystem of existing CNI plugins. There are really three main paths being considered, and each one has some pretty significant trade-offs. The first approach is that each CNI vendor, Calico, Cilium, Weave, you name it, ships their own bespoke DRA driver. The upside is they could expose all their unique features. The massive drawback? Zero interoperability. You could easily end up with two different drivers on the same node, both trying to claim and control the same physical hardware, which is a recipe for disaster. The second approach is to create a single generic CNI DRA driver that tries to be a universal adapter. This is simpler, but its limitation is that it can only expose generic attributes like PCI IDs or bandwidth, and it would struggle to handle vendor-specific features or advanced data planes. The third and most ambitious approach is CNI 2.0, which means fundamentally changing the CNI specification itself to include all of these advanced allocation concepts. This is the architecturally purest solution, but the drawback is enormous. Evolving a core, widely adopted standard like CNI is a monumental undertaking.
And this quote, which came directly from the Q&A session of the presentation, just perfectly captures the community's sentiment about that CNI 2.0 option. It's a bit of gallows humor, but it's rooted in truth. While a brand new, perfectly designed CNI 2.0 might be the ideal architectural solution on paper, the practical reality of coordinating such a massive change across dozens of independent projects is a logistical nightmare. The timeline would likely be measured in years, not months. This very real, practical constraint is why many in the community are leaning towards favoring solutions that extend the existing, stable CNI 1.0 spec rather than trying to replace it wholesale. It's a classic engineering battle between pragmatism and purity.
Another critical discussion that came up revolves around Multis, which is the current de facto standard for attaching multiple network interfaces to a pod. The question was basically, this is great, but why not just add all these features to Multis? And the presenters gave a very compelling answer. The problem with the Multis approach is that it relies on putting configuration data into Kubernetes annotations, and there is no standard for the format of those annotations. The way you'd configure a device on Google's cloud might be completely different and incompatible with how you do it on Azure or on-prem. The core argument for this new DRA-based approach is to escape that chaos by creating a true native Kubernetes API for these resources. This provides a universal, standard contract that every cloud provider, every CNI vendor, and every user can build upon, ensuring true portability for your applications.
And so, after this deep dive, we're left with this final, really thought-provoking question. The incredible progress being made with DRA, with resource claim status, with consumable capacity, it all represents a massive, tangible step towards true native multi-network support in Kubernetes. The pieces are finally falling into place. But it does remain an open question whether this current architecture is the final destination or if it's a powerful, necessary bridge that's leading us on the path to an even more integrated future. Perhaps a future that includes that elusive CNI 2.0 that our grandchildren might one day actually get to use. What is absolutely certain is that the entire landscape of cloud-native networking is being fundamentally reimagined right now, and dynamic resource allocation is at the very heart of that transformation. Thank you for joining us on The Explainer.